Moving in circles. Uniform circular motion is motion where an object travels in a circular path and maintains constant angular speed. Angular speed, or constant angular speed, means the object revolves around the entire circular path in the same amount of time each revolution. The period of rotation remains constant.
The rubber band exerts a force of constant magnitude on the dry ice puck toward the pivot point. The puck exhibits uniform circular motion. The rubber band exerts a force of constant magnitude on the dry ice puck toward the pivot point. The puck exhibits uniform circular motion. The rubber band exerts a force of constant magnitude on the dry ice puck toward the pivot point. The puck exhibits uniform circular motion.
If we're going to understand circular motion, we need a little background with circles. So our yellow circle here would be our circular path that this green object would travel around. And it could travel around in two different directions. It could either be going clockwise this way around or counterclockwise this way around the circular path. Notice that where the object is here, it's convenient to talk about the tangent to the curve. So this is the tangent line, which is also perpendicular to the radius. And so we'll be talking about that in a little while. It's also nice to know that the radius is from the origin of the circle out to the circular path. And we might want to know how far it is around this circle. And how far it is called the circumference. The distance around that circular path is the circumference. And the equation for circumference is 2 times the number pi times the radius, whatever amount that radius is. It would be a good idea to pause the video and note all this information in your notes. So let's exercise that equation for circumference now and see what we will get when we have real numbers and so forth. So we'll take our circle number 1 right here, and it has a radius of 0.4 meters. So this is our object cruising around this circular path. So how far does it go when it goes around once? So we take our circumference formula here, and we simply multiply 2 times pi times 0.4 meters. So you can use the pi key on your calculator, or you can use 3.14 for pi. And when you multiply all those together, you should have received a number of 2.5 meters around this circular path. And circle number 2 right here, same process. It has a smaller radius, and therefore after plugging in, you will get a smaller circumference, have less distance to go around. Pause and note these calculations in your notes. So now that we know how to calculate circumference, let's go ahead and evaluate the speed of an object that's in uniform circular motion. How fast is it going? Well, if you recall, speed is the rate of change of distance. So the distance we know is the circumference right here, the 2 pi r. Around a circular path. And the time right here to get all the way around a circular path would be the period of rotation, how long it takes to get around the circular path once. Pause and note these equations. Now that we know a little bit about circles and circular paths, let's take a look at 2 circles going around this circular path, and let's have them go clockwise. So they're going to start right here, and they're going to go all the way around and come back to here. Now this is kind of like a merry-go-round, and this ball and this ball, or this circle and this circle, both start together here, and they both go around together. And so when they get all the way back here to the start line again, they're together. In fact, they're together all the way around. But what is dramatically different here is their path lengths. So if we have a question here, how much farther is the blue ball moving than the green ball? And we look at those, well, we can remember circumference is 2 times pi times the radius. 2 and pi don't change in that equation. The radius is changing here. So if we double the radius from the green to the blue ball here, then the path length must have doubled. The blue ball is twice as far, goes around twice as far, the distance is twice as far as the green ball. That being the case, how many times faster does the blue ball have to move in order to get back in the same period, in order to get back to the same place at the same time? Well, quite obviously, if the time is the same for both of them to get around, then the blue ball must be moving faster, and since it has to go twice as far, it must have to go twice as fast. So we've seen that the blue ball would have to go around twice as fast as the green ball in order to get back around the same amount of time. Let's formalize what we could answer intuitively here by using our speed equation. Again, speed is the rate of change of distance, how much distance changes in a certain amount of time. And our distance, we remember, is our circumference. So in the numerator here, we can put circumference. And then our time it takes us to get around is the period of rotation. And so by plugging that in here, we get a new equation. Speed is the circumference divided by the period. Now typically we don't use this equation. We plug in for the circumference right away, and so plugging in for the circumference 2 pi r, we get our speed equation. The speed of an object in circular motion is equal to 2 times pi times the radius divided by the period. This is great stuff to take down in your notes. So let's do a sample problem and see how we can exercise our circular motion, our speed for circular motion equation here. And here's our word problem. How fast is the green circle moving with the radius of 2 meters if it goes around in 0.5 seconds? So our first process after reading the problem would be to circle and label our knowns. 2 meter radius. Now that's tricky because we've had meters as distance before, but in this unit it'll either tell us radius or it'll tell us distance from the center of a circle. So we have to know that that meters is a special distance, which is the radius. And it goes around in 0.5 seconds. Well, that's not regular time, that's a special time. That's the period that it takes the green ball to go around here, the period of rotation. And our unknown, fast, which is the speed of the green ball. So we do our KUF chart here, and our radius and period we note with 2 meters and 0.5 seconds. Our unknown is the speed, and we use our speed equation. V is equal to 2 pi r over the period. So 2 times pi times 2 meters, which is the radius, over 0.5 seconds is 25 meters per second if that was cruising around that fast. So that's pretty fast. Please note this. So now it's your turn. You're going to use the same equation and calculate the speed of the blue ball going around. Note that it is the same period of 0.5 seconds. Give it a shot and come back to the video and see how you did. So, how did you do? Hopefully you saw that really it's the same setup as the previous problem. The only thing that really varied was the radius here, and it doubled. Since that was the only factor that doubled, it would only make sense that the speed should double, and we knew that from before intuitively. So there's one last question to answer before we move on. Do the circles each have constant velocity? So we had the blue and the green circle. Did they have constant velocity? Well, it's kind of a tricky question because they had constant speed. The blue ball was going 25 meters per second around in its circular path, and the blue ball was going 50 meters per second around in a circular path. But those were speeds. Now we're talking about velocity, and velocity also includes direction. So this is just two different locations. So if now we have a red ball here in this location going counterclockwise, and at this instant in time it's going straight ahead. A moment later it goes off at a little bit of an angle here. So speed is constant, but since velocity includes direction and the direction is continuously changing here, no, the circles don't have constant velocity. They had constant speed, but their direction is constantly changing, and so they don't have constant velocity.
The puck moves on a cushion of air. Circular to linear motion. When the string burns through, the puck goes straight. When the force to the center becomes zero, the puck goes straight.
The velocity is changing direction. Therefore, the velocity must be changing and the puck must be accelerating.
So, in conclusion, we have our speed for an object in uniform circular motion is equal to 2 pi r, their circumference, divided by the period. And we just saw that the puck flew off tangent, so the direction of an object in uniform circular motion is always tangent to the circular path, perpendicular to the radius. And we also noted, since the direction is continuously changing, the direction's always changing, and acceleration is the rate of change of velocity. Since the velocity is always changing due to direction, an object in uniform circular motion is always accelerating. So pause and do a summary notation of this, and then we'll hear or see Scratch's parting thought. And Scratch's parting thought. And good luck on your quest for continuous improvement.